Hey guys, this is John. In today's video, we'll be talking about spheres. This is Recitation 8 in spring 2020, but this material is relevant to pretty much all semesters, but basically I'm just kind of recording this right now because of coronavirus. But anyways, so basically what we'll be covering today is the derivation and separation of variables, more leaning towards the separation of variables of Legendre polynomials, and then along the way we'll solve a problem and sort of apply the techniques that we have learned in the past, including orthogonality in multiple dimensions, multi-dimensional separation of variables, yada yada yada. The one thing that I think is important to note here is that although I'm deriving the examples from the textbook, specifically Haberman's textbook, his examples and descriptions for this particular part of the book are kind of bad in my opinion, especially in terms of separating the variables out and then providing examples on how to solve for the coefficients, putting in a general solution. So I will be detailing these in greater detail in the book. But before we get started, I think the first thing that I want to talk about is what's the point of Legendre polynomials in half-order Bessel functions. So I'm sort of giving away what we're going to find out later in this recitation, but Legendre polynomials and half-order Bessel functions are probably something you've discussed in class at this point, or maybe you've heard of them briefly. And their main application is in quantum physics or quantum physical chemistry, or in what's it called, quantum physics, or physics 361, 362 if you're taking those, which is like E&M. One of the biggest things that I've seen these come up in my other classes is spherical harmonics, and I honestly think this is pretty cool, right? Imagine like modeling an atom, right? This corresponds to the s, p, d, and f orbitals, right? That's pretty interesting to see these like come up in math, right? Like in Gen Chem, we've seen these come up since we were in high school, for example, and you're just like, what are these? What do they mean? And this is like the first class where you start learning how to actually find out what the spherical harmonics are. And basically, spherical harmonics correspond to Legendre polynomials. And in terms of like physics 361, 362, you'll be modeling potential on a ball. And yeah, I think this part of the book is very interesting. This part of the chapter is probably the most one of the most applicable to your outside courses. So hopefully everything I say here makes sense in some manner. Okay. So I think I'm gonna do start off this recitation a little bit differently, because the thing about spheres, especially spherical, the spherical coordinate system in terms of Laplacian is kind of messy. Like, I'll just go down a little bit and give away, but like this, I do not want to write this over and over again. I think it's counterproductive to our time. So I basically just wrote the derivation down below, and I'm going to work through each of the steps I took so you guys understand what I did. So in defining the problem, what we've done here is we are given this partial differential equation where we're trying to model the vibrations of a sphere. So you can essentially think we're trying to model the Earth, for example. We're trying to model like an earthquake on the Earth and try to modeling the vibrations across the entire sphere. We're also given a boundary condition at the outside of the sphere, which is telling us that we're equal to 0 on the outside, and then we're given two initial conditions on the sphere. So what I ended up doing was I drew the sphere that we're trying to model. So we can call this like Earth if you really want to, or Mars. I don't really care. And step 0, as per usual, is to draw a shape. So on the outside of the sphere, we're equal to 0, so the radius of the sphere is equal to a. And then we're going to be modeling this sphere in terms of spherical coordinates. One thing I do want to define in terms of spherical coordinates right now is what our variables are. Oh, this should be a rho. So in rho, our radial distance goes from 0 to a. I have defined theta to be the polar angle. So that's the angle that goes around the full length of a circle, right? Full degrees of a circle from 0 to 2 pi. And then phi, so phi is this thing right here, that's going from 0 to pi. So phi is going from, I'll draw this in red, from here down to here, for example. And that's what we're going to refer to as the azimuthal angle. In some other courses, I've seen theta and phi definitions switched up. So for example, phi would be from 0 to 2 pi and theta would be from 0 to pi. But for the sake of this derivation, I'm defining theta to be 0 to 2 pi, and I think it's very important to be able to distinguish between the two. especially because notations can get awfully confusing if you don't define them beforehand. So if you would use a different coordinate system than the variables I defined, I would really appreciate if you define them beforehand so I don't have to figure out what you're doing on an exam, for example. Okay. So in order to solve this problem, we're going to approach it via separation of variables. It's a homogeneous differential. It's a homogeneous diffie Q, so therefore we can solve it with separation of variables. Homogeneous diffie Q with homogeneous boundary conditions. Yes. Okay. So what I'm going to do is I'm going to let u of r. I'm going to underline orange. U of r theta phi t be equal to a product solution of w times h. So I'm basically just trying to get rid of the time dependence on this problem and put it on the other side of the equation. So in the following step, I have put all the time dependent terms on one side of the equation and then all the w terms on the other side. I'm going to set my separation constant equal to a negative number because I want my solutions in time to oscillate. Remember that we want oscillatory solutions because we're trying to model vibrations of a sphere, right? And vibrations are going to be oscillatory, they're going to be a wave. We wouldn't expect the vibrations to decay, essentially. We would expect them to decay if we had a dampening constant, but remember that we don't necessarily have one right here, especially considering this is just a standard old wave equation problem, essentially. So we're essentially modeling vibrations to infinity, so for infinite periods of time. So now I'm going to take the right-hand side of this equation and then equate it to each other. So nabla squared w is equal to negative lambda w. And then I'm going to do another product solution definition. So I'm going to define w to be equal to a composition of v of r phi times g of theta, okay? So now that we have the Laplacian spherical coordinates, which is given here, this is something you can just find in your book, basically. And considering the exams are open book now, this is just something you can copy. So this is what we call Laplacian phi and spherical coordinates. It's Laplacian w and spherical coordinates. So all I did was I essentially expanded this equation right here. And we know that's going to be equal to negative w because that's what we separated out. And then I'm going to plug in the product solution definition. So plug in w is equal to v times g. And all I did was plug in v times g across the board, right? So here, 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 here. Cool. So remember that our goal in separation variables is to put all the variables on one side and then put all the other variables on the other side. So what I did here in this step was I divided both sides by g. Divide by vg. So I'm just going to annotate this. Divide by vg. And this leaves us with v here, v blah blah g blah 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 blah, and then this gets rid of the vg on the right hand side of the equation. So we're just left with lambda. Okay. So I'm gonna stay here for maybe like 5 seconds. On this step right here. Can you guys see what we need to do next in order to isolate one of the variables? Hint: let's isolate theta first because that seems to be the easiest right now. Okay, that was your 5 seconds. We're going to multiply both sides of this equation by rho sine squared. And you'll see exactly why I did this in just a moment. So if we look at this term right here, notice that rho sine squared is the only non-dependent term on theta, right? So once we get rid of those, we'll have theta completely isolated, essentially. But also notice that, for example, like we have it also somewhat resembles this, and we can probably start eliminating the rho dependency on this term right here, because notice that once we get rid of the rho in the denominator, we're only left with psi, or phi, whatever, phi in the denominator, or phi in the entire part of that. So that's probably going to be helpful down the road. So multiply by rho squared sine squared phi. So in doing that, all I did was I essentially distributed across, and now we're just left with this nice term, which I'm going to circle in orange, that we can isolate on its own. Because if we look at all the other terms, they have no dependence on theta. So what we're going to do is we're going to move terms around. And in this sequence right here, all we have is theta on the right-hand side, g of theta, And then all we have on the left-hand side is v of r phi. Great. So now we've separated variables. So in looking at this, we have negative 1 over g times dg squared, second derivative of g with respect to theta. And we're going to set this equal to a separation constant that's positive. The reason why we're setting it to equal to a positive separation constant is because we have periodicity conditions in theta. So going back up to our sphere, since we have a full sphere that goes from 0 to 2 pi, remember the periodicity conditions. Periodicity conditions apply for a circle for the sake of completion. So just as a generality, let's call it u rho pi, oh god, I have to write all these out, pi t is equal to u p negative theta, so pi the phi t, and then there's the derivative condition, which I'll just copy and paste down. Theta, yeah, theta. Okay, so those are periodicity conditions, and from your table, you're given what the periodicity conditions are, so you should just be able to basically write table. Well, we'll solve all the diffie q's later, but basically this is a diffie q that we'll have to solve down the road. Okay, so since we have 4 variables that we need to separate out, we need to do another product solution to finally separate everything out. So I'm going to define VR phi equal to f of r times q of phi. So the first step I take to go from this step here to down here is I multiply by v and substitute. So by multiplying by v, I get rid of all the 1 over v's in the denominator, and I put 1 over v on this term. Sorry, I put v here and v here because they don't have v dependency originally. And then I substitute f and q in for the definition of v. So now we have fq, 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 fq. Great. I'll get rid of these arrows so it's not too confusing when you guys take these. I'm going to upload these on my website for notes, so let's just get rid of those. Okay. In the following step, we divide both sides by fq. In dividing, we get rid of all the fq dependencies here and here, but on the other 2 terms on the left-hand side of this equation, they're derivatives, and some of them you can't just cross out f. You can't cross out f here, for example, because f has a dependency on rho, but you can factor out q because q does not have any dependency on the derivative operator, so you can just factor it out. So consequently, you get 1 over f times sine squared, blah, 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 blah. Oh, I should not have done that. I don't know. Oh, there we go. Yeah, so you divide both sides by fq. And if you're confused about anything I've done along the way, please message me, email me, piazza me, or just go back to this video and walk through a little bit more slowly what I've been doing. But hopefully my logic is making sense to you guys. Okay, so now that we're at this step, we're equal to L. Hopefully we notice now that if we divide both sides by sine squared, eventually, we could... Wait, I don't know why. Wait, these 2 steps look the same. Oh, well, okay. Well, we're just going to ignore this step in the middle right here because I don't know why I put that there. But anyways, my point of emphasis is that if we divide both sides by sine squared, we should be able to isolate all the rho dependency on this term right here. We should be able to isolate the rho dependency because sine squared is the only non-rho dependent term. On this term right here, this is all dependent on psi of phi already, so that's good. And then here we can start isolating phi and rho dependent terms. Sorry, I get so confused between psi and phi. They sound the same. My bad. So in dividing both sides by sine squared phi. So I'll write this out explicitly. 1 over sine squared phi. We end up with this diffie q right here, which I'm going to mark real quick. This relationship right here. And what we should be able to notice now, I'll highlight this, is that this is only dependent on rho. And then this term is also only dependent on rho. And continuing the highlighting, this term is only dependent on phi, and this term's only not dependent on phi. So the nice thing we can do now is we can move all the variables to each side of the equation. So all the yellow highlighted, let's move it to the left-hand side of the equation, and then all the orange highlighted, we can move it to the right-hand side. So once again, going with the theme, let's copy and paste this up here. Oops. Okay. Move terms. Great. So once again, now we only have row dependency on the left-hand side and phi dependency on the right-hand side. So now we've successfully separated variables. I'm going to set the separation constant equal to mu, and the reason for this is we need it to be equal to positive mu in order to solve the differential equations that come up down the road. This would be very difficult to determine beforehand, and especially trying to make like an analysis like oscillatory or exponential solutions, because neither of these two equations are convenient enough for you to be able to pick that up immediately. But take my word for this right now, we're going to call it mu for now. Hopefully the reasoning comes out as we solve the difficuse. Okay. So step 2 of my usual method of solving things is to solve the difficuse. And just to briefly overview the difficuse we solved, I'm going to underline them in pink. This is one difficuse we're solving. That's the f of row that we're trying to solve. This is also another difficuse we're solving in phi. And then another difficuse we're solving is in g, which is here, which I'm going to do that. And then another difficuse we're going to be solving is h of t, which I'm going to do in purple. Okay. So let's solve for the differential equations in which we can solve for the values of the eigenvalues first, right? So the first one where we have homogeneous boundary conditions in both directions is g of theta. G of theta is bounded by periodicity conditions, right? So therefore, we can solve for its eigenvalues directly. So remember that given the differential equation g d squared dj theta squared is equal to negative g. I think it's L. Let's just double check real quick. Yep. The solution for this is given in our table. So this is just periodicity. And therefore, g of theta is simply equal to c1 sine m theta plus c2 cosine m theta, where L is equal to m squared. M starts from 0 to 1 to infinity. All right, so let's underline this as in green because this will be important down the road. Great, so now we've solved for g of theta. The next thing we have to approach now is we're going to solve for the q of phi function now. And the reason why I'm doing this is because with the help of the eigenvalue L, or the separation constant L, and knowing that it's equal to m squared, we're able to actually solve for the value of mu in this problem. So I'm just going to copy paste this down here. So this is the next differential equation we're going to solve. So this is obviously something you probably have not seen before. So it's a bit of a weird one, to say the least. But what we're going to do is we're going to move, I'm going to highlight this, we're going to move this term to the right-hand side. We're basically going to move everything to the right-hand side, basically to make the first term, which is this term, positive right here. We want to make that positive. So I'm going to move that to the right-hand side. And while I'm moving it to the right-hand side, I'm going to multiply both sides of the equation by q sine phi. And this will get rid of the q sine phi in the denominator. So in moving everything to the right-hand side now, we have 0 is equal to d phi sine phi dq. Since these derivative operators are only dependent on one term, now we can just do normal differential operators. d phi, continuing the multiplying, so plus u sine phi minus L sine phi multiplied by q is equal to 0. Let's just double check, make sure. Yes, okay. Remember that L from earlier, so this is the same L. L is equal to m squared. Okay, so let's pull this on here. So let's just make that quick substitution. M squared. Okay. So now that we have this equation so far, what we're going to do is we're going to do a not so obvious change of variables. We're going to change the variables into x, and the reason for this is we're trying to essentially get our differential equation into the form of Legendre's differential equation. Legendre's differential equation is not a true mathematical definition, but that's what I coined it, so that's what we're going to use. Okay, so we're going to let x be equal to cosine phi. And then we're going to change our differential operators. So remember chain rule, so d phi is simply equal to d dx d phi times dx. So we're trying to do a change of basis, change of variables into x. So this is the change in the differential operator essentially. And remember the derivative of x with respect to phi. Since x is equal to cosine phi here, we can essentially just do negative sine phi d dx. So let's substitute these two things into this diffy q now. So we're essentially substituting now, sub. So we end up with 0 is equal to negative sine phi d dx of sine phi times negative sine phi d dx q plus mu sine phi minus m squared sine phi q. So what I'm going to do is I'm going to factor out this negative sign here. So this negative sign cancels out this negative sign to make a positive number. I'm going to combine these two to make sine squared. So d dx sine squared phi dq dx. And then I'm going to divide both sides by sine phi. So I'm going to divide both sides by this thing. Divide. So we get rid of the sine phi on the front. And then we multiply through everything here such that we get mu minus m squared over sine squared phi q. So the last step we need to take is we need to do a substitution for sine squared here. Such that we get everything in terms of x. So remember the relationship that sine squared phi plus cosine squared phi is equal to 1. And then if we solve for sine squared phi is equal to 1 minus cosine squared phi. But remember that we define x to be equal to cosine phi. So in reality, this relationship is equal to 1 minus x squared. So now if we substitute everything in for sine squared in the top thing, we get 1 minus x squared dq dx plus mu minus m squared over 1 minus x squared q. And this right here is the key. This is what we're trying to find essentially. This is the reason why we did change of basis. This is why we separate the variables in the way we did earlier. We're trying to get this into Legendre. Well, I'm just going to quotation this. Legendre's diffy q. It's obviously not coined that mathematically or nor precisely, but this is the easiest way to refer to it. Okay. So why I call this Legendre's diffy q is because the solutions to Legendre's diffy q is a linear combination of p and q. So the solution to this diffy q can be written as a linear combination of these two solutions. C3 p n m of x plus C4 big Q and m of x. So this may be a little bit thrown at you, but hopefully the lecture supplements the more theoretical portion of what P and Q actually are. So these are called the associated Legendre functions. Legendre functions, also known as spherical harmonics, like the picture I showed earlier. And the interesting thing that is also thrown at you for this diffie Q, solutions, let's write that. The interesting thing that's thrown at you is that the value of mu, so this is just something that's given to you, you don't need to like explicitly solve it, and is equal to n times n plus 1 for n equals 0, 1, 2 to infinity. Okay, that's a really bad comma. Let's try that again. So these are the two important things you've got to take away from this. So I'm just going to repeat myself real quick. The solutions to Legendre's differential equation are in the form of a linear combination of p and q, and then mu is equal to n times n plus 1. So this n is obviously different from the m I've written earlier. So now we have essentially found the values of two of our separation constants. Okay. So to briefly overview Legendre polynomials. So Legendre polynomials, or associated Legendre polynomials, associated Legendre functions is probably the best way to talk about these. So what I mean by Legendre polynomials is when m is equal to 0. So obviously I haven't talked about the m equals 0 case earlier. So normally we place a lot more emphasis on when lambda is equal to 0. But the nice thing about this part is that Pmn basically covers for m equals 0 and then n equals 0 as well. So we're basically all set there. But for the m equals 0 part, our p function looks like this, like some integer n, 0, and this is what we refer to as the Legendre polynomials. Okay. The reason why I'm not really talking about q, let's quickly talk about q real quick. So p is bounded at both x equals plus 1 and minus 1. One sec, sorry. So I'm going to write this down again. P and m x is bounded at x equals plus or minus 1. And this basically translates to bounded at cosine phi cosine, bounded at cosine pi and cosine 0. So these correspond to the top and bottom of the sphere. If we quickly go back up, all the way back up, yeah. So what I'm trying to say here is at this portion, so let's call this cosine 0, and let's call this bottom portion of the sphere, let's call this cosine phi. So that's the azimuthal angle, the full range of the azimuthal angle. We essentially have boundedness conditions here, so this is kind of just like going a little bit into the theory of like what's actually happening here. So this has to be bounded here, and this also has to be bounded here. And the reason of this, what I'm trying to say here, is there's singularities at the top and bottom points. So we need to make sure that it's bounded. So sort of think about singularity condition at the center of the circle, or singularity boundedness condition, essentially. So these conditions need to be satisfied, so such that if we go all the way back down, Q is actually not bounded at those points, whereas whereas P is. So therefore, we choose to keep the P solution because we are it's bounded by the top and bottom. So P is bounded. This is the point to take away. Whereas Q is not. So we're going to drop the Q term and we're going to ignore it for the rest of this problem, essentially. Okay. So going on with this, we have for m equals 0, we've referred to them as the Legendre polynomials. So the Legendre polynomials take up a certain form. So if we take a look at n equals 1 or n equals 0, for example, so p0, 0 of x, this corresponds to 1. When n is equal to 1, p0, 1, x is equal to x, n equals 2. We have P20, so these are Legendre polynomials, so this is just the expansion of what they actually look like, and there's a whole table of these that you can just like Google real quick. Remember that we define x is equal to cosine phi, so in actuality when we're evaluating conditions directly, we get 2 phi plus 1, for example, and then n can go on to infinity. The general form is kind of gross, but I'll just write it out. Pn, so this is Pn of 0 is equal to 1 over 2 to the n factorial dn dxn x squared minus 1n. To be honest, this is something you probably don't need to really write down, because I feel as though the first few Legendre polynomials will be given to you, and you can probably just Google what they are anyways. So it doesn't really like matter if you have this formula down in your notes, but it's good to like get a sense of like what's happening. So remember that m can also be greater than 0. So for m greater than 0, we have the associated Legendre function. So this is like the parent to Legendre polynomials. Legendre functions. They kind of look bad as well. P sub n m, so for any m and for any n, equals 1 minus x squared m over 2 dm dxm pnx. So this last term corresponds to this function right here from the top. So if we quickly take a look at this, right, the thing we notice is that n has to be greater than or equal to m. So this is something very important we need to take away for our summations. So n has to be greater than m. And the reason for this is because if we take a look at the definition for the associated Legendre functions, which is here, with which I'm pointing at, and we zoom in on this term right here. So this is the term importance, which I'm going to circle in green. Notice that we're taking the derivative of a polynomial in n, right? So remember that we defined our polynomial in terms of n. If our derivative operator m, if m were greater than n, we would be taking a higher order derivative than n, right? So a more explicit example of this is like, let's say m was equal to 2 and n was equal to 1. So this would be d squared, dx squared of whatever the polynomial for n is. So for n equals 1, we have x, right? So this is m equals 2, n equals 1, and m equals 0, because this is Legendre polynomials. This is going to be equal to 0, right? So what we find out is that for Legendre polynomial, for the associated Legendre functions in which m is greater than n, those are all equal to 0. So in order to have non-zero solutions, we must force the condition that n is greater than or equal to m. Otherwise, if m is greater than n, then we would have everything be equal to 0 because of the simple fact on the derivatives. So the more general way of writing this would be to notice that dm of dxm is taking the derivative of a polynomial in m, and n, sorry, polynomial in n, right? So like just to repeat myself, if m is greater than n, we're taking a higher order derivative than the highest power in the polynomial, so therefore the polynomial just becomes 0, right? So that's a restriction we're going to have in our summation for our general solution. So this basically solves out the phi dependency. So now that we've solved for g of theta, we've solved for q of phi, now we can solve for f of rho. I'm going to scroll back up real quick and just copy and paste that differential equation down here. Boop, boop, boop. And that's all equal to mu, but we know what mu is equal to now. Mu is equal to equals mu is equal to n times n plus 1. Great. So we're going to move all the terms to the left-hand side. Hopefully this should seem like a differential equation we've seen before. I'm going to put these in terms of first-order operators because, because they're just taking derivatives with respect to one variable now. P plus rho squared lambda minus n plus 1 all times f is equal to 0. hopefully this sort of seems like Bessel's differential equation. However, it's not exactly Bessel's differential equation. It's like really close, but it's really not. And in order to solve this, so this is, we can just call this like almost Bessel's diffq. The main differences are the fact that there's this like p squared term here, and then but the solution for this differential equation is also just kind of thrown at you. So it's going to be the spherical Bessel functions. So it's going to be j in the order 1/2, such that f of rho is equal to rho to the negative 1/2. Actually, yeah, that's fine. Negative 1/2 times j n plus 1/2 square root lambda rho. Obviously, this is like kind of ugly, but this is basically the general solution for this differential equation, which is just kind of given to you. Yeah, you probably just have to take my word for granted. For this portion of MATH-241, you're basically given differential equations and their solutions. Actually solving for these diffqs is really difficult, so this is why you're given these like general forms of the solutions, if that makes sense. But yeah, you can probably just take my word for granted right now. The spherical Bessel functions can be related to some well-defined functions, but I think that's more of the purpose of lecture, to give you more of the theoretical sense of things. Hopefully that makes sense. Okay, so the nice thing about this problem right here is that we can actually find out what the values of lambda are. So remember the boundary condition given at the edge of the circle. So remember that at the edge of the circle will actually equal to 0. So we can get a direct relationship for the zeros of the Bessel function. And this gives us that the zeros of the Bessel function of order n plus 1/2, so order n plus 1/2 meaning the subscript right here, the lambda is just going to be equal to z m. We should call this. We have n m. Let's call this z sub n plus 1/2, so order z of n plus 1/2, comma, let's call it k, over a squared, where z subscript n plus 1/2 k is the kth zero of the spherical Bessel function at of order n plus 1/2. So this sort of notation should seem somewhat familiar to you. This is just the sort of logic that I apply for Bessel's functions in the first place. If you don't feel comfortable with what I'm saying right now, I highly recommend you watch my Bessel function recitation video, or look at some of the problems I solved for Bessel functions. Since this is the kth zero, we would start for k from equal to 1, 2 to 3. Great. So now we have a solution for f of rho. Oh, quick thing about in rho. Remember that we have a singularity condition. The singularity being at the center of the sphere, or like at the absolute center of the sphere. So like right here, singularity. So we also have an additional boundedness condition since we're inside the sphere. So the limit of f of rho as rho approaches 0 has to be less than infinity. And our y term still goes to infinity as it approaches 0, and j is bounded at 0. So we're going to keep the j term. Same idea for Bessel function, nothing new essentially. So let's quickly underline in green what we're looking for here. Doop, doop. Okay. Great. So now the last thing we need to solve is h of time. Hopefully this is nice and simple. We've been doing quite a bit of math. So htt is equal to negative c squared lambda h. Right. Since we want our solutions in time to oscillate, the general solution to this differential equation is just going to be let's call it like c5. I don't think we use c5. c5 sine c square root lambda h t plus c6 cosine c square root lambda time. But remember that we know the value of lambda, so we can essentially plug it in here, but that would be kind of ugly, so let's not do that just yet. But this is our general solution in time. So now our final, our next step in this problem, we're almost there to the finale, general solution. So this is going to be a very, very annoying general solution, to say the least. Since we have 4 variables, we're going to have 3 separation constants, and then since we have 3 separation constants, we're going to have 3 summations, 1 in m, 1 in m, and 1 in k. All right, so try to follow along. So remember that we define u of rho theta phi t to be equal to a composition of w rho theta phi t. Not t. Rho phi, yeah. Ht is equal to f of rho, g of theta, q of phi, and then h of time. Yeah, it's really long, so we're going to put everything together now. This is going to be equal to the infinite summation from m equals 0 to infinity. So there's going to be a very important catch that I'm going to put on here in just a moment, but just follow along with what I'm saying so far. N is equal to m to infinity, and then k is equal to 1 to infinity. All right, so why am I starting n from m? Remember the condition that we instated here earlier. For non-zero solutions to arise in our summation, the values for n must be greater than or equal to m. Values where m is greater than n all just become 0. So we don't want to conclude those in our summation. So this condition right here, this forces n to be greater than equal to m for all the possible values. So that's the purpose of instating this condition in summation. So now we're going to just essentially slap everything together now. Yeah, this is going to be annoying, so get ready. Okay, so we have a double dependence on time. So let's call this, so we can have a sub n, m, n, and k of sine c sub lambda, c lambda t, and then b, m, n, k cosine c lambda t. So the notation of these curly brackets is just like product solutions or matrix multiplication, essentially. Yeah, no, it's actually matrix multiplication. I don't know what I'm saying. So now we have to get our f of rho terms. So let's just copy and paste this down. Yeah. Quickly correct this. Rho n plus 1/2. Then we also need our Legendre polynomials, which we can just denote with p and m. Whatever. P and m. And let's call this from cosine phi. So we also need our g of theta terms, which are somewhat up here. G of theta is defined by sine m theta and cosine m theta. So we're going to have even more constants now. Woohoo. Yeah, so this general solution becomes kind of a mess when you have all these terms. So we're going to have c mnk cosine m theta, and then d mnk sine m theta. Actually, let me reverse this order so I can just stay consistent. So this general solution is obviously kind of disgusting. We're going to have, let's see, I think 8 terms. Yeah, annoying, I know, sorry. So the thing to note is that when we expand out this matrix multiplication, we're going to have to take the definitions of the constants m and k times c m and k, and we're going to call that like alpha m and k, for example, because they're arbitrary constants. The way I'm writing it right now is just to essentially put everything in the nicest, most condensed form possible. I'll quickly annotate everything real quick. So this corresponds to h of t. This term corresponds to f of rho. This term corresponds to q of phi. And this term corresponds to g of theta. So just to repeat myself, when you expand all this out, if you were to expand this all out, but for most problems you won't have to, because your general solution won't be this bad. You'll get terms like a times c, for example, but you can just redefine them as a new arbitrary constant, alpha m n k. Okay. So to sort of give an example of how to solve for these coefficients now, I'm not going to solve for all of them. I'm just going to solve for alpha m n k. So alpha m n k corresponds to the case of underlining in orange right here, sine. Obviously these terms right here, because these two terms in f and q are going to be across all terms, and then this term right here. Okay. Whew. So this is going to be nasty. Let's quickly bring down our initial conditions. Actually, let's not solve for alpha m n k. Let's instead solve for b m n k times, let's do c m n k equals, let's call that beta m n k. And the reason for this is I'm just going to evaluate this initial condition right here. And if I set time equal to 0 on the alpha m n k term, that sine term right here, which I'm circling, is just going to go to 0. So that I'd have to take the derivative, and that's just a pain. Yeah, okay. So let's evaluate at time equals 0. U of r theta psi 0 is equal to triple summation again. Oh boy, yeah, these problems can get really annoying, but thankfully you guys won't have to do a general solution like I'm doing right now. Setting time equal to 0, we only care about the bmnk term now. And then we're going to still keep everything else because those don't have any dependence on time. I'm just going to quickly erase this. All right, and this is, oh god, let's just kind of condense this a little bit more. Sorry, is equal to f p theta psi. All right, so in thinking of this in terms of triple orthogonality, so 3D orthogonality, multi-dimensional orthogonality, if you haven't watched my 2D orthogonality video, I highly recommend you do that. This will give rise to, so this coefficient that I'm solving for specifically is BC, so bmnk times cmnk, which I'm going to redefine as beta mnk because they're arbitrary coefficients, is going to be equal to something very long and annoying to write. So get ready. Okay. Okay, hyping myself up. So we're going to have 3 integrals, one for each direction. So for m, n, and k, we have 3 different directions in, oh, sorry, this term should go to 1, my bad, because cos at times 0. Nice, it got smaller. So we have to take care of the rho term, the theta term, and the phi term. So remember our rho term goes from 0 to a, so this corresponds to rho. Our theta term goes from 0 to 2 pi. This is our theta term. And then our azimuthal angle, or phi, goes from 0 to pi. So this is phi. So on the numerator, we're going to multiply everything by each corresponding eigenfunction. So f blah, blah, blah corresponds to this garbage right here times p mn cosine phi times cosine m theta. And then we have to make sure we're integrating in the appropriate space. So this is going to correspond to, I believe, r squared sine phi d phi d theta. Great. Then we also have to do a triple integral on the bottom. 2 pi 0a. This time we're going to square all the eigenfunctions. So this term gets squared. The Legendre polynomials also get squared. So we could evaluate all these directly, but that's a little bit too much work. So we can just write in these like condensed forms. Cosine m pi squared. R squared. Wait. Oh, I'm solving for c. My bad. So this should be sine. if I was solving for beta b d m and k, then the cosines would be there, but still sine phi d phi d theta. Oh, there needs to be a dr as well. Oh my god, so many terms. dr. Okay, so yeah, this would basically be your final coefficient answer, and then this would be also your final answer right here. Okay. So for solving for coefficients, obviously this is just kind of a rinse and repeat now. I can solve for any of the coefficients in any other style I want. So just to repeat sort of what I was just like briefly just saying right there. B, D, M, and K now. So let's call this, I don't know, let's call this delta, I suppose. That's an ugly delta. That's not even a delta. Well, let's just call it gamma. Gamma would just correspond to everything that I've just written, but cosine. Yeah, so this is just a rinse and repeat the cycle at this point. But this is how you solve for the coefficients in terms of 3D orthogonality, just thinking of it like how I just did there. You could also think of it more explicitly by applying all the like multiplication steps on either side of the equation, and then knowing that J and P are orthogonal to one another, or orthogonal to other J's and other P's respectively. But yeah, this is your general solution right here. But this problem's really long. For problems in the future that you'll see like this, you'll be given the information you needed to solve out everything explicitly. And when I say about that, what I mean by this is that you probably won't have to solve the separation of variables, but I have seen problems in the past where you have to solve out the whole, like you have to do the separation of variables and prove that the separation of variables works. So I would just be aware of like what could come, just to be safe, if that makes sense. But yeah, this is basically a very classic example of a sphere problem, going through all the steps. Yeah, hopefully that all makes sense. I think this video is a little bit shorter. I'll make some recommendations about how to approach these problems in future videos, most likely, and then on the next quiz, you guys will probably see a sphere problem. But anyways, I hope this video was helpful. Please let me know if you guys have any questions on Piazza, or email me. Yeah, stay safe, and good luck studying.